Hello guys, so today we'll be doing Machine Design Lab 8 Plasticity Analysis. So let's begin. So we're modeling I am modeling the beam that we were given on this diagram. I'm going to use 1.5 diameter for the whole rod and 1 centimeter diameter for this other rod over here, rod 2. So what will this look like? Let's just see. So I've taken the time to already draw the schematic on an isometric drawing paper, so it's easier to see. So you will notice that our rod 1 over here spans from this point to this point, which is 18. But this extra bit is not that relevant because the connection is at the point where it's at 16. You'll see over here that it's all the way 18, and this is 2 centimeters, 2 centimeters. So over here is our here to here will be 16 centimeters. Okay, so next part would be that our force F is not applied directly on the end of this beam or rod. Rather, it's applied 1 centimeter away from this end of the rod. Now there's a piece of the beam sticking out. This again is not relevant. This is just drawn for the sake of it compared to the diagram I showed earlier. So let's look at how we would model this in SolidWorks, at least the parts, and then we will see what forces to apply onto this parts and assembly that we will come up with. So we'll start with our rod 1. So we will start with let's say the front plane, normal, and edit sketch. And we want to draw, before we do anything, let's change, because for me I'm using centimeters, so I'm going to change to centimeter GS. So edit sketch, then doesn't matter, press enter. Then we have smart dimensions, and we click on it, and we want this to be our rod 1. Our rod 1 is 1.5 centimeters in diameter. Okay, so now we want to extrude this for 18 centimeters. So 18 centimeters, and we press OK. And this is our rod extruded. Now we want to cut a hole in this. Let's see approximately how much or where are we going to do this. You will see that over here. So let's zoom in a bit. If you look at this, we will have that our rod goes all the way to 18, but this point from here to here is 2 centimeters. And I said that this is 1 centimeter diameter. So if you imagine this is the hole right now, this is the 2 centimeter from the center. So our hole needs to be 2 plus 0 point. So this distance here to here, we also need to calculate. This would be 1 centimeter divided by 2, which is 0.5 centimeters. So this distance here to here is 0.5 centimeters. So where would this distance here be and this distance here? We'll find out in a minute. So that'll just be 2 minus 0.5. That will be our 1.5 centimeters, and the other way would be 2.5 centimeters. Okay. So now that's out of the way, let's see how we can add, or rather, if we can add a hole. So what we do is we click on Hole Wizard. That's fine. Now, Hole Wizard, and we go to click on Positions, 3D Sketch. We click on, let's say, we know it's going to be around here somewhere, so let's say around here. And then we know we want to make it go across, and we go back Type. We want the hole to be around, let's say custom sizing, we want the hole to be 0.5. So in diameter would be 1 centimeter. So 1 centimeter. Okay. Through all. Now, through all, 1 centimeter. Okay. Now we want to look at where we want this hole. So for example, let's see over here. Let's press over here. Okay. Then we can go down, dowel hole 1.5 centimeters, and yeah, okay. Through all, yeah. Option, that's fine. Press OK. Now we want this to be located at a certain distance. So let's look at this distance here. Let's look at this distance here, and over here, let's look at this point, edit sketch. So let's just look at how far away this thing is from here. So this is, for example, we want this distance to be 2 points. So from the center, and the end needs to be, let's look at what we said earlier. So we said that the distance from the center to the edge is 2 centimeters. So we're just going to write 2 centimeters back here. So 2 centimeters. So now our hole is 2 centimeters back. We click on back, and then now we know this. 2 centimeters here. We go back here. And okay. So, yeah, okay, done. Okay. Then we go features, hole wizard. We're outside the sketch. And now this hole should be 2 centimeters away from the edge. Like if we wanted to check, so let's maybe let's look at the plane of which plane is this? So this is maybe let's look at the top plane, and then let's go to the top plane ourselves. Edit sketch. Okay, here we go. So now let's check if this is 2 centimeters away. Get a line, draw a line, and this is around. Let's just say okay, and let's just do smart dimensions of this. This is just to check, by the way. This is just to check. So smart dimensions of this line, and 2 centimeters, and we know this is in the center. So we know we have done this correctly. Okay. So that was just to double check. So now we have our rod, and our rod for this particular rod 1, I'm gonna give it a material of ANSYS. So let's check. Exit sketch. So that's done. We can remove the sketch, and we can delete this. Okay. So now let's define the material. So edit material, and you need to go to, you can go to anyone that has this SS on the side. SS means that it has a stress strain curve. So when you click on stress strain curve, it has a pre-built-in stress strain curve, which is what we want for our plasticity analysis. So I'm going to go for ANSYS 135 steel SS, and I'm going to also need to note these values. I need to know the elastic modulus, I need to know the tensile strength, and I need to know, so not tensile, the yield strength, because we're trying to work out the force it takes to yield in our hand calculations. So we just need the yield strength and the elastic modulus. Okay, so let's apply and close. So this is my rod 1. I'm going to save this. Let's save it in a new folder called YouTube, and let's call this rod 1. Okay, rod 1. Now we need to make another rod, so Control N, and we need another part. So part 3, and again, similarly we did earlier, we're going to go for the front plane, normal. Before we do anything, let's change our units to centimeters. Then again, front, edit sketch. Then we get our circle. Doesn't matter what radius it is. Go to smart dimensions. Change this to, for me, it's 1 centimeter diameter. Now that's done. Go to features. Now let's look at how far I need to extrude my product or my rod. Is 16 plus 4, which is 20, but my force is being applied at 1 centimeters. So what I'll do is to give myself a point load, I'm going to extrude it 1 centimeters, and then I'm going to extrude it 19 centimeters. You'll see why. So let's extrude base, and let's extrude 1 centimeter from the base. Now, from this base, I'm going to extrude another time, and I'm going to extrude feature, extrude over here. Let's go. Exit sketch. Features, extrude. Hold on. Exit sketch. Extrude base. Another one. Okay. Extrude. Sketch. Convert entities. Yeah, sorry. Convert entities, features, extrude base. Then we're going to do 19 centimeters, and we're done for this part. Now, it's very important here that we do a couple of things before we do anything else. Now, with this, what you want to do is draw a couple of lines. We're going to draw some center lines. So why is this important? We're going to take this face, and we're going to draw a center line for this. So center line from here to here, and press enter. And we're also going to draw another center line for this. Now you'll notice that they have both of these extrusions have merged. We don't want that. So what we want is, let's go to our edit. Let's get out of the sketch. Edit feature, and you don't want to merge results. Okay, now we want to go back to our sketches, and I want to edit sketch, and I want to sketch another thing here. So exit sketch. So another center line, and let's take this face, and we're going to go from this point to this point. Now this is important. Why, you will see later. So this is a line. I did not want a line. I want a center line. So a center line between, so from here to here, and okay. Now we're going to go for features, and we're going to add some references from some references. Okay, exit sketch, some reference points. Now we're going to write this point over here as point 1. This will be the point we will be adding to our point load and when we do our study. Now we also need another point for our study, which is our vertex that we will measure our displacement from. So let's go again. Let's get another point, and let's click here, and that's another point. Oh, sorry. Let's press this back. Okay, that's done. Now press this point here, reference point, and that's the point selected, and this is our point. So there's nothing more to this except that we now have to add our material. So edit material, and I'm going to go for aluminum. So let's just get rid of the steel because, okay, aluminium. And I'm going to go for H18 rod SS. Why? Because again, I need the stress strain curves. So again, with this, we need the elastic modulus, note it down, and we need the yield strength, and we have to note it down. Apply, and we close it. So now we have our 2 parts, and now we have to make an assembly. So Control N, and assembly. So new assembly, rod 1. Oh, I did not save the previous part. So what I will do is, I'll go back and let's save this part first. Control S, rod 2, U2. Okay. So now let's go back to our assembly here, and let's add another component. We're gonna have rod 2, and that's it. Okay. So we have to mate these things. So let's go to mate this with this, and we're going to write concentric, and we're going to press OK. Okay, close. All right, what we'll do is let's get rid of these. So delete, yes, delete, yes. Okay, let's try again. Let's insert components one by one. So this over here, move it around a bit. Okay, and that is my rod 1. Okay, so let's go over here and insert another component, and we're adding rod 2. So again, we're going to move this around a bit, and that's okay. Now we should be able to move it. Yes, okay. We should, one component 6, that's fine, but this component should be able to move. All right, so now we click on mate, click on the circular face, and this hole over here, Okay, so we want to lock rotation, and we're done. Now you'll notice it's still sliding, so we need to put a distance limiter in the advanced options. So what we're going to do is, before we do anything, we need to know the distance that we need to put this away from. So for me, if you look over here, that, again, let's just get another side view on this. So maybe let's change color here. So now we're looking at this face on. So we have over here, we have this face here, and we have a rod going through it, right? And this rod is like this. So this length over here is supposed to be, from the center, supposed to be 16, right? 16 centimeters. Now this diameter here is 1.5 centimeters. So, and this is 4. So what do we need to do? We need the half of each. So this is 0.75 on this side, right? So from this face, I have to put 4 minus 0.5. So this distance here would be, from here to here, would be 3.25 centimeters. And if you were taking the other side, so this point would be 16 plus 0.75. So this from here to here would be 16 minus, yeah, 16 minus, so that would be 15.25. Okay? Okay. So I'll show you what this means. So I'm going to click on this face over here, and I'm going to click on this concentric face, this circular face. And I'm going to click on my distance limiter, and I'm going to change, I didn't even change my centimeters, so I'll change that now. So I need to click on 3.25 centimeters. And you'll see that it has gone to exactly where I want it to go. So now this is what I wanted. Okay, let's go to maybe an isometric view. Maybe around here. Okay. So you can take a screenshot of this as well. So now what we have is, what's left is we have to do the study. So you go to simulations, new study, and if let's say you don't have this enabled, you will have to go to SolidWorks add-in in your parts, and then, so if I go to my parts over here, oh, let me press OK, let's go back to parts now. So you should have SolidWorks Premium Simulation or SolidWorks Premium, and you should have the Simulation Premium version of it. Otherwise, it won't work. You'll get some errors. So let's go back to our assembly, and let's start a new study. So SolidWorks Simulation, new study, and you go down to nonlinear, and this is static analysis. So press OK, and we have these things. So before we continue, we need to know the force we're going to put on this beam. So now let's go to our hand calculation that we need to perform. So let's look. So we have the following information from the SolidWorks. So I'm going to write them down. So we're going to assume that rod 1 we set is rod 1. The material we set is ANSYS 1035 steel. And then we said for our rod 2 is 1080, yeah, H18 aluminum. Now I think it's 1080. Let me double check. Parts, and 1060. Sorry, 1060. So let's change that. 1060 aluminum. Now I'll write the following properties for these, taking from the SolidWorks. So you'll get So our yield stress for rod 1 is 282 point, so I can go back, 282.69 Newton per millimeter squared, which is again MPa. We also are given the E of this elastic modulus, which is 204,999.9984 Newton per millimeter squared. Again, that's MPa. Okay, some other things that I assumed. So these are things I assumed. So there are my diameter for rod 1, I assume to be 1.5 centimeters, which is equivalent to 15 millimeters. Okay. My length that I'm going to use for rod 1 is 18 millimeters, right? Now, is this the length that is necessary though? Is this the length that we're supposed to use, you might ask? This is, in fact, not the length we're supposed to use. We're supposed to use a different length, right? Which is at the point at where we're acting from. So at the point of the connection. So from here till here, where our connection is. This is the only length we consider. So the length we're going to consider is 0. This is our 16 centimeter. We're not going to consider 18 centimeters. This is just an extra bit I added. We don't need this for our calculations. So our calculation will be for 16 centimeters, which is 160 millimeters. Okay. Now, our next, for rod 2, what are we given? So let's look at rod 2. I'll do this in blue. So the yield stress is already given from our SolidWorks, so Newton per millimeter squared MPa. Elastic modulus is given as 69,000, Newton per millimeter squared, so Newton per millimeter squared, which is MPa. These are things I assumed. D2 is 1.0 centimeters, which is 10 millimeters. Our L2 is equal to, now let's check. Now the L2, the whole length is 16. But the point of what we're acting at is, let's call it A, and you'll see why I call it A in a minute. So L2 is 16 centimeters, which is 160 millimeters. But our A is 150. 150, or let's be specific, 15 centimeters, which is 150 millimeters. Now, I know this, that I have to write A because I have to use the Cantilever intermediate load formula. So if I was to show you, oh, hold on, not this. If I was to show you from the Shigley's book in table A9, go to Cantilever beam 2, and I'm going to maybe just, oh, not this way. Maybe if I Control V, let's shrink this. So we're given this information. So in this we have that our A is at 15 centimeters. So this is what we're going to use to work out our deflection. Okay? So let's just note this down for future, because we will use this in the future. So let me do it in green. Our delta will be F A squared A minus 3L over 6EI. Okay. So now that's done. Let's work out the force needed to yield for this object, for this part. So what were the stipulations that we were told? We were told that we have to assume that rod 1 is rigid and rod 2 is yielding. Then we have to assume the other, that rod 2 is rigid and rod 1 is yielding. We will discuss what happens in both the cases. So before we do anything, we need to understand that these both rods are subjected to bending stress. So bending stress, formula is the formula is MC over I. right? Where our moment is our force, let's call it F1 times L times L, right? And our C is the diameter divided by 2. And our I for circular cross sections is pi d squared over 64. Okay, so now let's work out the second moment of, let's work out the I for both rods. So for I1, that will be pi, d is 15 for the first one, so 15 squared over 64. Let's bring out our calculators over here on the side. So we have shift pi over 64 times by d squared, which is 15 to the power 4, sorry, not squared, obviously it's 4. My bad. To the power 4 and to the power 4. Let's change that to the power 4. So let's go back and 4. And we get this is equal to 2485.05 millimeters to the power 4. Now let's do the same thing for I2. Pi d to the power 4. Our d is 10, so 10 to the power 4 over 64. Let's check what this is. So 10 equal, and we get 490.87 millimeters to the power 4. Okay. Now let's work out the moment for both of them. So we can rearrange this, because what are we trying to find out? We're trying to find out F. The only way we can find out F is if we find this, then we can rearrange to find F. So when we rearrange to find M, that is our yield stress times by I over C. So we want to work out moment 1. So M1 will be equal to our Y1 times by I1 over C1. Okay. So what is our yield stress for the first rod? And we're assuming rod 1 is obviously ASI 135 steel, and that is 282.69. So we're going to write 282.69 multiplied by 2485.05 all over C1. Now we use the diameter of C1 is 15, so we can just have 15 over 2. So let's look at what moment we end up with. So I'm going to just go up, press equals, and then answer times 282.69 over 15 over 2. And we get 9393666.46 Newton millimeters as our moment M1. Now let's look at M2. Again, we're going to use the yield stress for aluminium, I2 over C2. So we will get sigma Y2 is equal to, if you go scroll back up again, that will be 108. So that's what we're going to use. 108 multiplied by 490.87 over 10 millimeters divided by 2. And let's check what this gives us. So I'm going to go up, let's press this equals again, and I'm going to write this and just change the top and bottom values. So 10, and this I have as 108. And I get 10602.88. 10602.88 Newton millimeters. So now I have both moments. I can work out both forces that will yield, that will cause yielding. So how do I do this? I know that M is equal to FL, so F is equal to M over L. Now let's check. So our moment for, let's break it down to, let's find out F1 for rod 1 will be M1 over L1. So our moment for the first one is 93666.46 divided by 160, right? So this gives us a yield of, so if I go back up here again, okay, so 93666.46 over 160. This gives us a F1 of 585.4 newtons. Now, let's look at F2. M2 over L2. Now, this would be, again, this L2, this is where the bending is occurring, so this will be our A, or this won't be our L2, just to be clear. So this would be our 10602.88 over, and now it's not 160, it's 150 because the force is acting at 15 centimeters away, not the whole bar of the length, not the whole rod length. Okay, so we divide it by 150, and let's see what we get. So 150, scroll up again. So 10602.88. This gives us a value of 70 point, let's say, 7 newtons. So which one will be the yielding force? It'll be whichever one is the smallest of the two. So the smallest of the two is F2, 70.7 will cause the yielding to occur. So that's what we have. So now we have found out the yielding, and this is, now we're done with the hand calculations for yielding. Now we can input this force back into our SolidWorks. So let's go back here, and what we need to do is add a fixture. So fixed geometry, we're going to go for this hinge here, and let's be a bit careful. Good to get rid of this for now. Delete, make sure you're applying it straight, and that is our fixtures. Now our next thing we're going to do here is we need to apply a point fixed load. So external load, force. Now you'll notice I can't directly click this. What you can do is you can go down, and for rod 2, go down, click on point 1. Now you can click on point 1. That's what we wanted, right? Now, the force we're going to apply is 70.7 newtons to see whether it yields or not. Then we're going to go, we need to select the direction, and let's look at which planes that we can look at that we want to apply the direction in. So if you look at the front plane, this is parallel, so we don't want this. The top plane is, yeah, so the top plane looks like that it can work. And now what I'm going to do is I'm going to click this icon over here. This is normal to the plane. I want it to go downwards. So let's say over here, let's reverse the direction. So it'll be on this end. So you'll see this is now very similar to what we have over here. Now all we're going to change is the units of this. So 70.7 newtons, that's what we're going to change. Okay, that's done. And now that we have what we wanted, now we should get, oh, we didn't work out the deflection. I'll go back to it in a second. So let's press OK, and let's create a mesh. Create mesh, and I'll just keep it just a bit more fine, because it will take a bit of time, but it will be a bit more accurate. Press OK. Now we need to run the study. So yeah, let's run the study. Whilst the study is running, you'll see that it'll take a bit of time. We'll go back to our calculations, our fixtures. Okay. Unable to create plot because cannot be formatted. Also, you can modify the quantity type under and return the study plot requested. Let's go to nonlinear properties, and if it's too high, then what we can do is let's make it 0.1 for the steps, and press OK, and rerun the study. Now it should be working. You'll see this is in steps, is increasing in steps, and it will keep on increasing, and then you will see a result quite soon. The more number of steps you have, the more accurate this value, the more accurate answers you'll get. Now, what we're after is the displacement, and let's look at, okay, time times time, okay. All right, let's chart options, let's go to floating, and press OK. And we're still getting different answers. So have we fixed everything? This is the point load, yeah. Let's go over here, edit definition. Top plane, let's put this to 0, put this to 0. And let's go up again. And force, like per item, yeah. Force, yeah. Okay. Instead of negative, let's reverse the direction so it's positive. And what we need is, yeah, I think that should be fine. Let's rerun the study and see what we get. Okay, so we're still getting values which are very tiny. What we can do is maybe let's increase the force or increase the step size. So most likely let's increase the step size. So nonlinear properties, let's make it maybe instead of 0.01, 0.05. And let's just put this option here as well. Press OK and run the study. So while that's happening, let's go back to over here and calculate the deflection, which we did not calculate. We found the force, so we can calculate the deflection now. So whilst that's happening, we have the deflection is equal to F A squared A minus 3L over 6EI. Right? So our deflection will be 70.7 A squared, which is 150, squared 150 minus 3 times 160 over 6EI. 6E, oh, well, it was that huge number, which you can obviously round, but I'm just going to use the values that were given by SolidWorks. 204,999.9984. So 204,999.9984, and we multiply this by I. What was I for sigma 1? I was 2485.05 to 2485.05. So our sigma 1 will be, or delta 1, sorry, not sigma. I don't know why I keep saying sigma. Okay. So 70.7 squared, not squared, sorry, times 150 squared over 150 minus. Now, this will give a negative answer, so how about we just change it so it becomes 3 times 180 minus 150, and then all over 6 times 204,999.9984 multiplied by 2485.05. Let's press equal, and we get this is 0.202. So with this force, rod 1 deflects with this much millimeters. Now let's look at rod 2. So FA squared A, so instead of A, let's just put 3L minus A over 6EI equals, now for simplicity's sake, I made sure for my assumptions, L1 was equal to L2 for me. So the calculations are easier for me. That's the only reason. Now obviously you can change these L1s and L2s for yourself, and you'll get a different answer. So A is 150 squared over, we will get 150, sorry, 3 times, yeah, 160 160 minus A, which is 150, all over 6. Our E is 69,000. Our I is, let's go back up again, 490.87. So 490.87. So our delta 2 or deflection 2 is, so let's just, only thing we're changing is these values here, so let's just go back quickly. 6 times 69,000 multiplied by 490.87. Scroll up, we will get 3 times, oh, I pressed 180 last time, so let's just go back, hold on. I see, let me just change this to 160 real quick. So 0.171, so let me change that for you guys. So that will be 0.172 millimeters. Okay, let me go back up again. So here, only thing we're changing is the bottom half because my values for lengths are the same, multiplied by 490.87, and you get 2.583. So 2.58. So no, 2.583. 3 millimeters. So our total deflection of the entire beam, or that entire beam, entire part would be 0 plus, so this plus 0.172, 2.755 millimeters. So this is what we should expect, or something similar, or maybe not so similar in our SolidWorks. Okay. So the issues we're getting still are, let's check. So let's just save everything. So Control S. This is assembly. Okay. No. All right. So let's just look at what our issues were. Let's just see if we can get factor of safety plot. Okay. Generate. So maybe we'll have to just run the study again. So if I just run the study again, but this time maybe if I can change the properties and increase the step size to maybe 1. Let's see if this works. Press OK, and we will run the study. Okay, so it's running now. So over here. So it takes a bit of time, and you'll see afterwards what we can do with this. We will do some more studies, which are already pre-done for you guys, so you guys can just see what you should change for each study. Because we were told to do a displacement control analysis and a force control analysis, so to determine at what displacement the yielding occurs. So the way we do this is you will see if I add or create a new simulation study after this is done. So once this finishes, we can start. Just give it some time. Might not load fully for you guys if I can. What I wanted to show you guys was that you can see the step size here. That's what's happening over here. Still, we can't really seem to see the deflection. Maybe the force is too small. Let's look at our displacement and let's look at our stress. Still nothing. Okay. So, for example, let's look at our factor of safety plot at least. So, factor of safety plot. That's okay. And this is still being a bit weird. Okay. Alright. Now let me show you the ones I've already done, and we can compare them to this one. So let's look at the force control analysis, the ones we had here. So what I did over here was I added a force of 200 newtons. 200 newtons over here. You can see over here I had a force of 200 newtons. And then the results were as follows. So we had a stress. So this was the stress given. So if I maybe go over here. So these were the results I got for the von Mises stress. I got 293.54 megapascals, and for the displacement I get 79.41 for 200 newtons. for 200 newtons. If you just to compare, if we were to make this 200, so the only thing we're going to change is change the force for 200. So if we go back here and the calculators and go up, yeah, okay, this, and then the only thing we're changing is our force. So let's take plus fraction, and instead of 77, let's just put 200, and then we have the same thing. So 6 multiplied by 69,000 multiplied by 490.87, and it's 200 multiplied by 150 times 150 times 3 times 160 minus 150, and you will get that it should be 7.79. So if we use the force of, let's say, 200 newtons, we should get a yield stress, a deflection of 7.79. Theoretically. This is theoretically. Okay. So what do we get? We get 79 millimeters. That's a factor of 10 difference. That's huge. That's huge. Now, why could that be? That could be due to the fact that this particular material yields after that and now becomes a bit different, right? So the force distribution of this material changes drastically as we increase the force. So let's just look at a couple of things we can see here. The factor of safety, it's obviously 0.92 is the lowest, and that's the lowest. So this is most likely what we're looking at. Another thing that could have happened over here, if you look over here again, is that what could have happened is, if we go to the nonlinear study, let's just see if I can just double check something. So we did fixed support, yeah, we did the external load, we did this, reverse, okay, properties, maybe go to advanced, let's just increase this to the equilibrium let's say, no, one step is fine, tolerance, okay, alright, and go to, okay, let's try again, run a study. So okay, still very small. Okay, still don't see the issue. 78.7. This is still fixed. Nodal stress. Pictures. Yeah, should be fine. Yeah. Did we lock the rotation? I think we locked the rotation. This should be fine now. Rod 1 is ASI and rod 2 is this. The load that we get is also the same. So what to finish the study and we're still not getting the same answers. That's interesting. Yes, it's 100 now. So maybe let's increase the mesh, so create mesh. Okay, let's create the mesh. Let's make it extremely fine. Press OK. Okay, that's the mesh done. Let's rerun the study. So it'll take a bit more time, but at least what we'll get is accurate. Because maybe the mesh size is not as we'll see that. Okay, the number of nodes is quite high. Maybe it will take quite a bit of time to finish the study. Okay. In the meantime, I will show you the other study I've already done and what it'll look like. So what will happen is, this is still running, right? Yeah. If I go here, no, selector, I guess. I'll wait for command to finish. I'll just close SolidWorks to see. Okay, restart SolidWorks. Yeah, okay. Starting SolidWorks. Simulation, okay. Let's just open the parts again that we had open earlier. Let's look at this for a second. Let's look at the assembly we had. And yeah, okay. So let's look at the let's do the study. Maybe that was the issue. Let's try again. Assembly, SolidWorks, simulation, new study, linear, press OK. Then we have our fixtures, fixed geometry. Press this OK. Is this fully fixed? Yes, it's fully defined, cannot be moved. Okay, cool. Then we do our external loads, force, this from, and you can see that force, the point will not be selected. So what you can do is you can go down, click on point 1, in selected direction from the top plane, and we will do, and this is normal to the plane. Let's put 200 newtons just to check if we get what we get. 200 newtons, reverse the direction, and press OK. Create mesh, press OK. And now we should just run the study. This should work. Any error that we get, we will look at. Okay, yeah, so now it's working. Okay, so I don't know what the issue was earlier. Let's see what we get, and I'll change the value to 270.7 newtons, and we'll see the factor of safety plot that will be given. So the plot step means how much of the step size of 200 is this current force. So for example, if you had 10 steps, then the 8th step would be 0.8 times 200, which would be 160 newtons. So right now we're at 75%. Oh, 70%. That was just 75 right now. Oh, and 60. Oh, it's just decreasing. It'll take a bit of time. The higher your value for the force, the more longer it take. So that's why I took a very small load in the beginning, and I took a small diagram so that the force that we need to apply isn't that large. So that way it'll be easier to do. Okay. Give it some time. And once it's done, that'll be good. Okay. Because there's another study we can do after this. This is the force control. The next one will be displacement control. I want you to compare the two together. If you do run into a runtime error, whatever value you get for your time, it will be written here. So for example, for now, it says 0.7125 to step 14. This is what you're going to use in the next part that I'm going to tell you now. So, where is it gone again? SolidWorks, 72%. So we still have a couple more steps left. The number of steps depend on the number of nodes you have. The more nodes you have, the more time it will take. Yeah, but it's obviously more accurate answer. Okay. If you just click on displacement plot for a second, you'll notice it's getting close to a value we should get. For example, this value should be around 7.79, right? if it jumps from 7.79 to like a massive number, we already know that it's past its yielding point. So now it's just behaving erratically that we cannot control. So let's see. So still 0.78 seconds at the moment. So we still have a bit of time. Oh, this is times 10 to the power 1 though. So this will be 48. So it's already way past our value. So while this is happening, you can start on your report. You can start writing, taking pictures of what we need. I'll open. Actually, no, I'll not open because maybe you'll just crash the current SolidWorks study. Just to review. So the things you can change are the diameter, the length, the length, the length, the force value, the diameter of the other rod that you'll be taking, so the small diameter over here. These are the things you can change, and obviously the material and this material, which will give you different values. So you'll get this value, you'll get the solution in a step greater than 1. It could be due to the fact, so if you go back here down here, it could be due to the solution being at a buckle point or limit point, and you just press OK. And you'll see that for this particular study, the time stopped at 0.781348 seconds. So at this particular step, the displacement was around, so if we look at our chart options, go down, scientific floating, let's see this definition. So we can't go any higher than this. Look, this is maybe if I go back, displacement, chart options, I can't increase this step size. I can't increase the step time to 1, which we should have 1, but we don't have 1 at the moment. So chart options, scientific floating, press OK. So this is what we have at the moment. We have 48.9, so maybe over here. So let's see if we can see it better from this angle here. Okay. So this is what we have for our displacement. Now we also want to get our displacement, no, factor of safety plot, and we'll press OK. You'll see that the factor of safety is 0. So settings, again, chart options, scientific floating, and it's 0.85. Now, this is consistent with what we know, that it does yield after, so at F equals 200, we know that a factor of safety, which is this over what you have, should be less than 1, which is true. So we know that this, in fact, is not 0.9, 0.85, which is consistent with what we found. Oh, however, this displacement, however, is not consistent, right? So another thing we can do is, this was, if I rename this study, this was the force control, so force control study. Now, if we duplicate this, so if we, what is good to note is this thing. So 0.781, so if I'm going to write down over here. So for the time taken for 0.781348 seconds, I got a displacement of 48.957. So 48.957. Now, the thing to note here is we duplicate the study, so copy study. I'm going to name this study displacement. So displacement control study. Press OK. And the only thing we're going to change here is we're going to change this definition, and we're just going to write this as 1. I'm going to keep this as 1, press OK. And then instead of having -1, let's just change the direction. So it's positive, so we can see a nice graph. Okay. Then again, we're going to change something here in the properties of the displacement, the study itself. So properties, Now we're going to change it to displacement. So you go to advanced options, click on displacement, and we need to click on this vertex, the vertex that is going to displace the most, which is this one over here. So either this both are the same. Or actually, rather, let's just before we do that, after this I'll change the force to go downward so it's the accurate as it can be. So the way you click on this, you'll see that you can't click on this directly. Again, you can go down here over rods, and you can click on point 2, and this is the point over here. So we want this in the direction of y, right? And then edit, and we're going to change this to what we had earlier. So we had 0. So if you go back here, 0.781348, so 0.781348, and the displacement we got is 48.957. Ideally, you want this value to be 1, and you want this to be the value you got. Now I'll press OK, and I'll press OK, and I can run the study. But before that, let me just change this to edit definition and just make it go reverse direction. Press OK, run the study. Whilst this is running, I will open. Oh yeah, you'll get this error. This is fine. You can just press OK. You can just press OK. So press OK, and then this will continue. And whilst it's continuing, I'm going to open the other file. So we had the other one, which was I think the new assembly. So this one over here. I'm going to just click on this, open with SolidWorks launcher, and this will open whilst the other one is going on still. So this is still going on. So an error occurred while trying to open your file. That's fine. Let's go back to YouTube and open our assembly. So come on, assembly. Okay, assembly, and I'm gonna open the other assembly as well at the same time, and then I'll run the study, and then I'll just show you at the same time. So that's what we're going to do. So this. Oh, did we not save it? Hold on. Ah, we didn't save it. Okay. Let's go back here. So let's go here, YouTube, control study, SMT. Nice. Okay. Let's go back here. New assembly. Okay. I'll just explain from this because it says the same 200 newtons, right? So what you should have gotten for the force control analysis is, if you look over here, is let me change the view. So over here, let me. Okay. This is what we have. This is the stress induced, but this is at This is at step equals 3. We don't want this. We want the step at equals 1. So let's edit definition. We want this at 1 second. So 1, press enter, press OK, and you'll see, so the other way around maybe. There we go. Okay. So this is where it went. So this is the force. Let's just quickly change the definition, pascals, and we want chart options to be floating. Press OK. So we get 293.54. This is our force analysis, force control analysis. And we also want the displacement. So the displacement is at, again, this is at plot step 13. We don't want this, so let's click on settings. Definition at 1, press enter. Chart options is already done. General, let's do floating, and press OK. So we get at 79.407. This is obviously the total displacement. If you're after just the displacement of the delta 1, so rod 1 or rod 2, the rod 2 probably, because that's the aluminum rod, we can add another plot here. Click on this, add displacement, and we want just the y displacement, and we press OK. And we're gonna see that that is chart options. yeah, here, scientific floating. Okay. Oh, not centimeters. Start options, definitions, millimeters. Okay. So just comparing them. So this is 77.235. This is 79.407. So the rod 1, so if we just compare this, so let's go down. So for F equals 200 newtons, we get a total of 77.235, 77.235 millimeters, and we get just the y, just in the y direction, we get, oh, that's 77.235, the other one's 79.407. So let me just quickly click on this, bring it down, and Control Shift V, and that is 79.407. So you can see that the other deformations, the torsional deformation, everything else is attributed to the subtraction of both these values. So quickly get the calculator. 79.407 minus 77.235. So 2.172 millimeters of deflection is due to, for example, the torsional effect. We also have something called the section modulus, so that's also, you can use that to calculate these values earlier. We can also have other effects. So for example, over here, we didn't apply mesh control. So for example, this also might have been attributed to the other values, difference in values. Okay, so that is for force control. Now we're going to just rename this. So if I'm going to click on this, I'm going to rename this as displacement control analysis. So the way this works is, right, you'll see, and you go to displacement control analysis, properties, you go down and click advanced options, and you'll see, for myself, I've already clicked on this. This is 0.74, so this was when I was doing it, 0.74919, and this gave me 17.404, right? So if I cancel this, press OK, go here again, I know my displacement, my result displacement was for 1 second, 79.407. So if I go back, click this, properties, 79.407, advanced options, edit, 1, 79.47, and press OK. Graph. This is what it will do, and we'll see what happens with it. So press OK, and then we run the study. Study will run rather quickly. We don't want the stress. We want the, for example, you'll see in real time what's happening to this over here. But I want the displacement. So let's go back here. 32% done. You'll see that there's another thing that we can put in our result options. That's called the load factor, and we'll see how that's important. So almost done. Once it's done, we'll click on the load factor. This will give, and I'll tell you how we can get this load factor as well. So it's done. Okay. So another thing we will find out from this is something called the load factor. Now, since we put a 1 newtons, we will find out for the same deformation how much force is actually required. Okay. So let's go down here, and is it done? It's still doing it. 82.84.6. So you'll notice this is now we are around 68.5 millimeters. We know that we had 79 79.407. So if it goes past 79, that's an issue, right? Not an issue, but it's more like it's showing us that there's still discrepancies in reality compared to FEA simulations. What we did earlier when you assume it's just a linear model and that obeys Hooke's law, as opposed to when it's plastic. Okay, you'll now notice that we have, let's go to displacement. Let's look at chart options and definitions. Millimeters, chart options down, floating, press OK. We have 81.806, the other one was 79.407. So there's still a difference. There's still a percentage error between these two. Now, if you calculate the percentage error between these two, this is not really significant. So again, you'll be doing it for no reason. Now, the other thing I said I was going to show you, so if I delete this and I show you this plot, you go here, click on time history plot, click on all nodes, and then click on Y displacement, and that's it. Press OK. You will see this nonlinear response. You will see that starting from this displacement here, that we had 1 newtons, so it takes 199.26 newtons to come to the same load that we set, and the load we set was 200. So there's still a discrepancy, right? And you'll notice the graph, it changes rapidly after this point here. So for example, if I put a value 150, I'll get something around here. So for example, I'll get maybe let's go 150, and scroll down. You'll get a graph like this, and that just shows that it basically yields around here, and then it changes its response and becomes like this. This is the material itself. Now you can do the same analysis for changing for steel and for aluminium. Okay. So let's just save this before we forget. Okay. And now what we can do is we can compare results. So we can compare results for all studies. So for study, and we want all studies, we want displacement. And before we do that, let's go back. Let's double check this. Okay. What's wrong with this? What's wrong? Okay, that's fine. Close. Stress. We just want to compare results. Okay. Yeah, no, not this. Exit compare. So when you click on compare and you click on all studies, the force control is not showing you because the current results are not there. If we just run the study quickly, if it doesn't, then I'll show you the image I took earlier. Over here, I'll just show you the image earlier, which I took. So data modified type, I should get VD2, VDF, JPEG, yeah, this one. So you should get something like this. So when we're comparing our this one and this one, so this is for my force control analysis over here. This is for my displacement analysis over here. You'll notice that for the same stress, we're getting, for the less stress, we're getting more deformation. So this is a more accurate representation of what happens in reality than using a force control analysis. So this is what you need to get out of this lab. Okay. So at the end, you can compare this and that's your worry. Okay. So this can keep on going, and it'll just take a bit more time. So it will get the same results because it's 200 newtons. So good luck. This was a bit longer video, but hopefully it works out. All right, good luck. Bye-bye.